All right. Settle down. We can talk about that after class.
I avoided a problem.
Okay. Hopefully that test was better than the first one. Before we begin, just mentioning homework 12.1 due tomorrow.
Tuesday.
Yeah.
When did I say Tuesday?
Yes.
Tuesday, you said Tuesday.
It's on video.
No, it's tomorrow.
Yeah.
Come on.
It's tomorrow. 12.2. Just going to basically tell you the main idea here. Double integrals over general regions. Okay, so this might spill into tomorrow, but I'll give you the essential idea here. Basically, this chapter is going to tell you that you can set up a double integral over region D in one of two ways, where D is not necessarily a rectangle. Alright? But often, you'll be able to set up this double integral in one of two ways. There's the way when you set up dy dx. And there's going to be the way when you set up dx dy. And here's how it's going to look. On the outside, you're going to have two constants. You're going to have something like a and b. On the inside, though, you're going to have two functions. Let's call this g1 of x up to g2 of x. For this one, a similar thing is going to happen. On the outside, you're going to have constants, say c, d. On the inside, you're going to have other functions, say h1 of y, h2 of y. Notice that on the inside, I have functions of x when my dy is on the inside, right? Because my y I think of as a function of x, right? So these guys have to match up, right? X I think of as a function of y, those guys have to match up, right? It's not really mentioned in this chapter, but I'll tell you now. Anyway, this idea generalizes. Right, so for example, we're going to be looking at triple integrals soon. So for example, if I have an integral that looks like this, it could look something like a, b. And then here I would have, say, g1 of x, g2 of x, matching with the y, and then on the inside, I can have h1 of xy, h2 of xy, right? So z is a function of x and y is a function of x I consider to be a constant. It's very important that the order goes in this way. It always looks like this, right? So if you have a triple integral setting it up, triple integral would be dv. Constants are always on the outside. Constants always here. Right? So your dimension 0 guys go on the outside all the time, right? Curves go here, curves, right? This means dimension is 1, right? So the first dimension goes here. Surfaces would go on the inside, right? So your dimension is 2, right? And of course, hypersurfaces would be the next one if you're doing a fourth derivative, right? So here you have constants. Here you have a single variable functions. Here you have two variable functions, so on and so forth. Right? So that's important that at the end of the day, when you set up an integral, that's going to be the relationship. Right? You're always thinking of as constants on the outside, single variable functions on the inside, double variable functions on the inside, then triple variable functions, and so on and so forth. Every time you move inside towards an integral, you add a dimension and you add a variable, right? So you think of these things in different ways, right? So for example, if I have a triple integral, f of x, y, z, dz, dy, dx. And let's say I have 1 up to 2, 1 up to 2, 1 up to 2, right? Now these guys all look like constants, but it's very important that you have the concept that these are not really constants, right? These here, you think of these as just constants, real numbers. However, the 1 here, you think of it just as a constant. But when 1 is here, how are you thinking of it? As a function, as a curve. So this 1 here really represents a horizontal line. Right? What does the 1 here represent? A plane. Right? So it's very important that you think of these in the right dimensions. Right? So I'm saying here they are constants, here they are functions, here are surfaces. Right? That's going to be a very important idea. It's going to help you set up these integrals, right? So the things on the limits, they mean different things. It's possible for you to have a function with no variable present. So a constant function is completely legit. You just need to know when you see a 1 here, it's a horizontal line. If you see a 1 here, it means something different. See a 1 here, it means something different again, right? You need to understand the dimensions.
Is the plane on the inside integral described by the line x equals 1 and 1?
Yes, it's described by the variable here, for example. So this you can think of it as the plane z equals 1 and z equals 2. Right? Here you can think of this as the line y equals 1 and y equals 2. And here you have x equals 1 and x equals 2. Right? So the variables will tell you how you can set up the function. That's also going to be very important. Right? So basically, this, what I just wrote here, describes a rectangular box for my region. Right? So in the xy plane, I'm going to get more specific and write this down more specific soon, if not now, tomorrow. But I just want you to get some basic ideas down on how you want to think about these integrals when you see them. So the last integral describes this region. Let's say I'm in the xyz plane, right? It means my x goes from 1 up to 2, my y goes from 1 up to 2, right? So when these guys intersect, they're going to form a rectangle. Right? And then I'm going to let my z go between 1 and 2. So what's going to happen is there's going to be a plane cutting across here. So what I'm really describing is this box, which now it's sort of, let's make sure I get this perspective right. Perspective is totally off. So me setting up that integral is like me integrating over this box, right? Where my x values runs between 1 and 2, my y values run between two functions 1 and 2, my z values run between two planes 1 and 2, right? So setting up that region is sort of like me telling you, integrate on this box, right? So now in 3 dimensions, we're not just integrating on intervals anymore. We can integrate over regions and we can integrate over solids. Like I'm going to describe a solid to you and say, find the integral on this solid, right? Which is, now you're going to realize why 10.6, the one where we learn how to graph all these surfaces, matters, right? Because there are going to be times where I'm going to say, okay, take the surface, intersect it with that surface, cut it off by this surface, integrate on that, right? You're going to need to be able to figure out how to set up these limits. So what you're going to do is you're going to draw things because the order of the numbers are going to matter. So the constant here, if it's with x, the left constant would go here, the right constant up there, right? The bottom curve would go here, top curve would go here, bottom surface goes here, top surface goes there. So you're going to be able to have to draw your surface and figure out, okay, on top I have this, on the bottom I have this, on the left I have this, on the right I have this. So you're going to need all that to actually start to describe these surfaces. That's sort of the main idea behind these. And we'll get used to this idea as we go on. But basically that's it. I mean, so if you ever like set up an integral, and I see a constant inside here and a function outside here, right? Like if you set up an integral like 2x to the 1 and 0 to 3 of x squared y dx dy, right? Like if I see that, I know you have no idea what you're talking about, right? I'll just give you a 0 and move on with my life, right? Constants always go on the outside. Functions always go on the inside. Surfaces always come after that. It will never be the case where you have to switch these guys around. Constants always here, right? So, right, this is nonsense. Right, so if you set up anything like that, you're wrong, right? And totally wrong, way wrong. Okay, so what this means is, and like I said, I'll describe this in detail soon, but since we only have 20 minutes, I just want to get the basic ideas out of the way that we can sort of rush through. So for example, if I see an integral like this, 0 to 1, and then I have this guy goes from 0 to 2x, x squared y, y dx. Right? Basically what this means is you're thinking of this region, right? You can sort of see this as the region here, right? Y goes between functions, so your y would go between 0 and 2x is what you're saying, right? These are, you think of them as functions, right? Your x value goes between what and what?
0 and 1.
X would go between 0 and 1. Therefore, the region that you're integrating over, what would it look like? It's going to be a triangle, right? So this region I'm actually integrating over would look like what? Well, I know my x goes from 0 to 1. Those are constants. As far as I'm concerned, those are points on the x-axis. Now, what is my y going between? 0 and 2x. Now, this 0 I don't think of as a constant. I think of it as an entire function. So my y is going between this function, which is running along the x-axis, and also this function, which is a line running through, right? However, I have a boundary on my x's, so it means this is getting cut off. And so this is my actual region, right? Now, the important thing is, you need to be able to go either way. If I describe a region to you, you should be able to set up the integral limits. And if I give you the integral limits, you should be able to figure out what region I'm talking about, right? It's going to be important for you to know how to go in both directions. So basically what you're going to be doing is, you see, okay, the y is on the inside, which means I'm thinking of these guys as functions. I'm thinking of the function 0 and the function y equals 2x, right? So I'm going to figure out, draw y equals 0, which is the entire x-axis, and draw y equals 2x, which is just a line going through the origin, right? Here, x equals 0 is a constant, so just a coordinate on the x-axis. And x equals 1 is also a constant, right? But that gives me my x bounds. So y is between this and this, x is between that and that, and you sort of combine them to figure out the region. So this integral is being done over a triangular region. Here's a challenge for you. Switch the order of integration. of that particular one, yes. Right, so here I have 0 to 1, and I have 0 to 2x, x squared y, dy dx. I want you to switch this to some integral of x squared y, but instead I want you to set it up as dx dy. Could you do that?
No.
You can. Didn't you say that?
The order matters.
Now the limits are not going to be the same. Now remember last time we spoke about in 12.1, when there were just constants here, you could switch them and not worry about it. Now if I put functions on here, it's different. You have to worry about it now, right? So if I give you this, and I say, change the order of integration, right? You have to figure out, well, what am I integrating over? Well, this is really going to give me this region. That's my region D, right? Now notice I let y go between 0 and 2x. I let x go between 0 and 1. These guys I'm thinking of as functions. These guys I'm thinking of as constants, right? Which means if I want to switch the order of integration and put x on the inside, what does it mean the x has to go between now? Two functions. By switching the order of integration, I'm just switching their roles. Now I want to figure out how do I describe this region so that the x goes between functions and the y goes between constants. Right? The same region. Can I describe it alternatively? Yeah, well I look at this function here, y equals 2x, which means I can say x equals y over 2. Right? What is this function here? That's just the function x equals 1. So what do you think is the range on x here? What's the lower bound? Y over 2. Remember, lower for x is on the left, right? So if I look on the region, who's on the left? This function is on the left. That's my description. So y over 2 is going to be the lower bound. Right? Who's on the right? X equals 1. 1 is going to be on the upper bound. Right? Now my y value goes between constants. What would the constants be?
0 to 2.
0 to 2, right? X is 1, y is equal to 2x, which means when x is 1, my y value is 2. And so now I would describe my y as going between 0 and 2, and think of those as constants. And therefore, when I set up this new integral by changing the order, so what are the limits now? On the outside, I put 0, 2, inside, y over 2 to 1. Now it's very important. When we're talking about x, remember we're thinking horizontally. So x, you always put the left on the bottom, the right on the top, right? So you need to sketch your region and figure out the positions of these things in relation to each other. Who's on the right, who's on the left. Left goes on the bottom, right goes on the top. For the y, the bottom guy goes on the bottom, the top guy goes on the top, right? So the bottom constant was 0, the top constant was 2. For the bottom constant here, the top constant there. So x goes from left up to right, y goes from bottom to top, right? It's just sort of the horizontal and vertical measurements. So even if you figure out these two functions, the order that you put them in actually matters, right? Because we learned back in Calc 1, when you switch the order, you actually take the negative of the integral. So it can actually change your answer, right? That's the basic idea, right? That's going to be, and you're going to realize that there are some times when changing the order is going to be important. Did I give an example? I did give an example.
You did. What was the example?
Wait, what time is it?
10:30, 10:40.
It's 10:40. Okay. We'll stop there. This is the basic idea. Again, I'm going to go over this specifically next time. But have these ideas rolling around in your head so that next time when I give you all these definitions, you'll understand what they all mean. 12.1 homework due tomorrow, and we will pick up with
Oh my God, thanks a lot.
12.2 from there. All right? Bye.